All right, so this is lecture 17. I'm going to talk to you about chain rules here. The organization on page 290, rather 192 to 205 of the 2020 lecture notes is essentially to study chain rules for when we're composing a function of several variables with a function or a vector of functions that is a function of just one independent variable first, and then we deal with two independent variables second, and then finally more than two independent variables. And also, the chain rules here are considered ultimately for the outside function being real valued for the most part until the very end of the section, where I then deal with the outside function actually being a vector of functions. So every single chain rule that we'll look at in this section at some point or another in this course we'll come back and use, but we'll probably focus mostly on the case of one independent variable and a function of two variables just to get started. So here's the basic thing. If we differentiate a function of xy that's been composed with a path, right, x of t, y of t, then the way the derivative works, it turns out, is you take partial f partial x times dx dt plus partial f partial y times dy dt. In other words, you can look at the derivative as the dot product of the gradient with the velocity vector to the path. Now, technically speaking, this is a little bit of there's some omission going on here, right? This gradient of f actually has to be evaluated at the point x of t, y of t. And this dr dt, of course, has to be evaluated at t. So just like the ordinary chain rule, back in Calculus 1, we have to take the derivative of the outside function and evaluate at the inside function. That still happens here. But anyway, likewise, if you had a function of n variables, you have this chain rule. So basically, the chain rule can always be restated in terms of like gradients dotted with velocities, so to speak. All right. And so to start with, before I say anything else, I would just point out that that's pretty neat because, if we had a parameterization of a curve, and so if we just had x and y here, it would actually be a level curve. But if there's x, y, z, this could be a level surface. But the point is if the curve is if the parameterization is is a parameterization of the curve, or if the parameterization lies on the surface, then that means that when you plug the parameterization into the equation for the surface, you get back 0, or a constant if we're setting it equal to a constant. So then the chain rule says that if you differentiate that composite, well, then it's the gradient of the level function evaluated at the path dotted with the velocity of the path. And so that goes to show you that claim that we've seen before, which is that, for example, level curves have tangent vectors which are perpendicular to the gradient vector field to the curve. So the chain rule proves that, essentially, is all I'm trying to get at here. All right, so let me get into the notes. Oops, don't want to get ahead of the story just yet. We'll get back to that eventually. Lots of examples in the notes here, so I probably don't need, but probably, I can add examples, of course, but I don't think there's a need. So I start with just the case of, this is from the chain rule we saw for space curves before, right? If we reparameterize the curve, then the velocity vector gets multiplied by the derivative of the reparameterization. One of these light bulbs is kind of, I think it's that one. When these light bulbs are about to go, they start kind of oscillating. It's getting on my nerves. Sorry about that. So, for example, if we had that path and we reparameterized with sine t rather than t, in other words, we replace t squared t cubed with sine t, sine squared t, sine cubed t, then when we differentiate, we end up with, basically the derivative of the original in terms of time, replaced with u, times the derivative of the inside function, which this time is cosine t, and when you work it out, you get that. Of course, you'd also get cosine t, 2 sine t, cosine t, 3 sine squared cosine t, if you just directly substituted sine t into the, into the path and then differentiated, right? So we've already seen that chain rule actually. But, you know, my sense of organization, I have to put them all together. So next, this is the new one. If we consider the composite of a function of two variables, all right, then here's the rule. The derivative of f of r of t is partial f partial x dx dt, partial f partial y dy dt, which we can rewrite as the dot product of f, the gradient of f with the velocity. So this is important. The independent variable, we need to learn this language, okay? The independent variable in this example is t. All right, the intermediate variables are x and y, all right? And so that's the typical pattern. We have, when we differentiate a function of several intermediate variables, where we're viewing those intermediate variables as functions of time, as a function of the independent variables, then the chain rule is a sum of partial derivatives over the independent variables multiplied by corresponding derivatives of the independent variable of the intermediate functions. Anyway, the sentence I just said you don't have to necessarily remember, but it would be good for you to know the terminology independent versus intermediate, all right? I'll keep using that terminology to try to drive it in. Again, so a more pedantic statement of the above chain rule looks like this. Notice that, like, the partial derivatives also have to be evaluated at t, like that. So here's an example. So suppose we have f of xy is x squared minus xy, and we're given that x equals e to the t, y equals t squared. Then when we differentiate, you know, f df dt, all right, then that's partial f partial x dx dt plus partial f partial y dy dt. That's the chain rule. And what that looks like here is 2x minus y, that's partial f partial x, right? This guy, is that the guy. And do some color coding here. This guy is just that e to the t, right? Because remember, x is e to the t. And then over here, the dy dt is coming from t squared, and that's why that picks up this 2t right here, right? And the partial f partial y, well, that's exactly this minus x term, right? Because when we calculate the partial derivative with respect to y of f, we just get minus x. And then what that means, right, is that you can plug back in x equals e to the t and y equals t squared, and you get this lovely expression right here, all right? So I'm sure you might think, well, why don't we just plug in e to the t and t squared into here and just differentiate directly? Won't we get the same answer? Well, yes, we will, but there's many theoretical reasons that you need to understand the chain rule. Like one of them I just showed you in terms of the perpendicular normal vector versus tangent vector. In fact, I think that's probably going to be my next example right here. So this I just shared with you already, but here's the, just in 2 dimensions. I wrote it for n dimensions to be confusing, but in 2 dimensions, if you have a level curve and you have a path which parameterizes the level curve, then the geometry between those two is revealed by the chain rule. We differentiate the level curve composed with a path. Chain rule gives us this to be explicit. That's the gradient evaluated at the path, dotted with a velocity to the path. But remember, this has to be constant if it's a level curve, right? So if this is equal to 0, that means that the gradient is perpendicular to the velocity, which of course we have seen in many examples, right? So as it's what the next paragraph says is like, this is an arbitrary, this is an identity for any function. But when we think about what it means for a level curve, it gets interesting. All right. Moving on here. So I guess part of my point in that example is just to show you that we don't always have formulas for x of t and y of t, and yet we have said something interesting. So you really do need to understand the chain rule. You can't just kind of dodge it and always evaluate things. All right, another example if we have, and oftentimes we use z equal to f of xy in this section, just like we use y equals f of x in, like, pre-calculus and calculus. So in this context, z, let me write out some things. In this context, z is the dependent variable. And here x and y are intermediate, the intermediate variables. And in this context, t is the independent variable. All right. So we can calculate a derivative of the dependent variable with respect to the independent variable, with the understanding that the independent variable is actually built from a composition of, the intermediate variables as a function of the independent variables. And I'm saying variables, but what I really mean is a composition of functions, right? So, like, the chain rule here is partial z partial x dx dt plus partial z partial y dy dt. And so, in particular, these are the partial derivatives written in terms of the intermediate variables, and then times the derivative of the sine t and cosine t there, see? Now, and then to put the answer as an explicit function of the independent variable, I then substitute back in what x and y are in terms of time to get an answer explicitly in terms of time. Now, I don't always ask for you to do that. Sometimes star is actually the answer. That's probably what I'm saying. So I say the boxed answer has xy expressions explicitly written in terms of t. Right, keyword there is explicit. Okay? Explicitly written in terms of t. In contrast, if we were happy to just have an answer written in terms of t as well as the x and the y, the intermediate variable, then this answer up here, this star line, could have constituted the answer. In fact, a lot of times when I ask a question on test 2, I will say something like, calculate the partial derivative. You may leave your answer in terms of both the intermediate and the independent variable. And I say that because it's actually much easier to see what you guys have done if you don't make the extra step. Because once you guys make this extra step, then you'll start simplifying. And it's very easy for it to get very complicated in terms of the grading there. But anyway, so like I said, as a point of brevity in some tests, some instructors allow a star-style answer. The complete thought, though, of course, is that that star answer is paired with, x is sine t, y is cosine t. All right. Anyway, let us agree that, if I say to give the answer explicitly in terms of t, then star is not the right answer, right? But if I say that you can leave it implicitly in terms of t, notice the word implicitly. Implicitly would be the star answer. Explicitly would be the boxed answer in terms of, being explicit functions of time versus up here implicit functions of time. Okay, now I think there's your vocabulary lesson for the day. Let's see here. Excuse me. Let's go on here. So suppose you have z equals xy, and you want to calculate dz dt, given that x is equal to e to the t and y is equal to sine t. So structurally, this is pretty much the same as the previous example. So we get partial z partial x dx dt, partial z partial y dy dt, and here's the answer in terms of the implicit, and here's the explicit answer. All right. Okay. So, and then at this point I say, okay, well, if you more generally had a path where it was in terms of x, y, z, and you're looking at a function of x, y, and z, then you could calculate df dt as partial f partial x dx dt plus partial f partial y dy dt plus partial f partial z dz dt if there was a function, if you had 3 intermediate variables, and those 3 intermediate variables were also parameterized as a function of your independent variable, in this case time, or t, and still it would be the gradient of f dot dr dt, but these are 3 vectors this time, right? And again, to be fair, that boxed equation right here is an abbreviated form of what's really true, which is that you're differentiating the function evaluated. It's a composite, right? The chain rule is about a composition of functions. So f of r of t is what you're differentiating, and so you have partial f partial x evaluated at the inside function r vector of t, which is really x of t comma y of t comma z of t, and then like so. So do you really want to write all that out? Well, I don't know. I mean, sometimes writing that out sort of informs what kind of derivative you're doing. Like for example, let me just show you what I mean. Like I know what chain rule to write down. If somebody tells me, what the kind of describes the function you're differentiating pretty carefully, then that will tell me what kind of chain rule I should do. Let me show you. I mean, like if somebody said d dt, and then you had f of, let's say x of t, y of t, z of t, and maybe there's even a 4th variable, w of t, Right? If somebody tells me that, then I know what I need to do. I need a term for each intermediate variable, x, y, z, and w, and each one of those is it's multiplied rather, with the appropriate derivative of the intermediate variable with respect to the independent variable. It's like that. And then one of these guys, and then one of these guys, and then one of these guys. So to capture the entire change in the function, you have to account for how the function can change in each of the intermediate variable directions. And each one of those is influenced in turn by how that variable has been parameterized, let's say, with respect to the independent variable. And that's the chain rule. And that's how it works. All right, let's keep going. All right. So here's another example. This time I've got a path in 3 dimensions, and if intermediate variables x, y, and z, so that means I get 3 things, three terms in the chain rule. And here's the implicit answer using intermediate variables. So like partial f partial x is 2x, partial f partial y is 2y, partial f partial z is 2z for this function, right? And then the dx dt, the dy dt, and the dz dt are based on, this is my x, right? This is y, and this guy right here is z, right? Oh, I've written it right here. X equals that, y equals that, z equals that. And then, of course, you could plug back in what x, y, and z are, and then you could even simplify it and and get 0. Why is that? Why is that derivative 0? Do you know? Think about it. Why would that derivative be 0? Maybe, just maybe, this path is a parameterization of a curve on that surface. If we said x squared plus y squared plus z squared equal to a constant, that defines a level surface, and maybe this is a path on a level surface. In fact, if you calculate x squared plus y squared plus z squared, you notice that the sine squareds, cosine squareds add together to give you 1. So you end up with when you end up with 1 in total, you can prove that x squared plus y squared plus z squared equal to 1 for that path, which means that this is a parameterization of a curve on the sphere. And so, of course, the gradient vector is going to be perpendicular to the velocity vector, which is why we get 0 there. All right. Now that's just one of many, many curves on the, on the sphere, right? Okay, we'll come back to that. But that actually is an important idea. It's like, on a level surface, you got lots and lots of different paths, each of which the gradient vector field to the surface is perpendicular. So like, I'm not sure exactly what that thing looks like, but it's, I'm not trying to be, careful here. I'm just saying that there's some kind of path. I think it's a great circle. This point maybe is R of t, right? And the gradient vector field to F would be like perpendicular to that, Oh, my picture's not great, but you get the idea. Anyway, let me stop drawing bad pictures and move on here. Okay, so next example is just kind of an abstract example. Basically, I point out that if you have any, function of three variables and you compose it with a path, you get this, right? And if that path actually parameterizes a surface, a path on the level surface, f of x, y is equal to k, then we've got that the gradient of the level surface at the path dotted with the velocity vector, the path is 0. So, all right. Now, I say a little bit more. I say, okay, so the gradient vector field is normal to the tangent vector field of an arbitrary curve on the surface, and it follows then that the union of all such tangent vectors forms the tangent space to the surface. Maybe that deserves a picture. That probably deserves a picture. All right, so what I'm saying here is, you've got some kind of surface, right? And this surface maybe is defined by f of x, y, z equals to some constant, right? And then if we fix our attention on a particular point, like let's say here, then we can look at different paths which go through that point, like this one, right? And what that calculation shows is that the normal vector to there's just one normal vector at that point, right? Which I'm going to draw like this. This normal vector, right? Which is the gradient of f evaluated at that point, right? I'll call that point P for the sake of discussion. Well, that is perpendicular to the velocity vector to that red path, which maybe I could draw the tangent line like that, But the thing is, that's true for any path that goes through that point. See, because there's not just one path that goes through the level surface at a point. There's many, many, many paths. And so I can just as well, think about the path that looks like this, right? That path, and that path also will have a velocity vector, which is, perpendicular to the normal. And so if you start, just keep doing that and start thinking about, all possible tangent lines through the point. If you take the union of those, then those are going to eventually fill out this kind of plane which possibly lifts off the surface, which is called the tangent plane. So we can think about the tangent plane as being formed from the union of all tangent vectors at the point. And those tangent vectors are perpendicular to the normal vector field formed from the level function to the surface. This is usually what we can do. Now, there exist surfaces which are not nice, which don't, allow for this like smooth characterization, but we're not going to talk about those. I mean, you could talk about those if you wanted, and they're not hard to come up with examples of surfaces which, don't quite fit calculus, at least at one point. Like here's one. Take a piece of paper and do this, all right? Right there, that point's trouble for calculus, right? So a cone is something that kind of escapes this discussion. However, every point except for the pointy point on the cone is okay. So anyway, so I just thought it would be good to add a picture there, and now I have. And so here I argue that if you take a sphere and you could look at it as a level surface, and if you calculate the gradient to that, you get this vector, which you can easily see is pointing in the direction. It basically points to the points away from the center of the sphere, right? And the equation to the tangent plane at that point, x naught, y naught, z naught in the sphere is this. And so, yeah. Well, anyway, there's an example. Let me move on here. We'll talk more about tangent planes in a later section, all right? So let's not belabor that too much here. So next up, yet another example. 3 intermediate variables, x, y, z, and then we're parameterizing them in terms of t and t squared and t cubed for x, y, and z. And again, we get, partial w partial x plus partial w partial y plus partial w partial z multiplied respectively by dx dt, dy dt, and dz dt. Excuse me. So like this right here would be the answer using implicit functions of time. Or you could say it's the answer in terms of the intermediate variables and the independent variable time. And of course, we could simplify that down to 6t to the 5th, which is not surprising, right? Because if you multiply t times t squared times t cubed, you get t to the 6th, and the derivative of t to the 6th is 6t to the 5th, right? All right. And then finally, so if we have a function of n variables and we compose it with a path on Rn, then we get this, general chain rule. And so here's a mnemonic, a memory device, if you will, that some people, not me so much, but some people like this. And in my notes, there's some color coding, so let me try to recover that. So basically, you can draw your dependent variable at the top, and then you draw your intermediate variables in the middle. And the idea is to form the chain rule, you have to go through like all possible paths, going top to bottom, and as you go down the path, it tells you how to make the formula. So like that. So there's just 2 terms for functions of 2 variables if there's just 2 intermediate variables, but if there are 3 intermediate variables, then you got this path, you got the path through y, so to speak, and I think some people call these tree diagrams. I don't know. Call them whatever you like. I don't like them, but I'm sharing it with you because it helps some people. So there you go, and that kind of is a way to remember how to form the chain rule in terms of the dependent, intermediate, and independent variable. And then my next example discusses the geometry of the general chain rule, which I'll let you read. So, in fact, I'm going to go on here to 2 independent variables. So 2 independent variables. We're going to use u and v. U and v for our 2 independent variables. And I wrote this out on a separate paper, so let me get that paper here for a second. And then we'll go back to my notes. I will eventually find that paper. Here it is. So if we have 2 independent variables, let's say u and v, and we've got a function of x and y, then we can partially differentiate the function composed with the 2 intermediate variables as a function of the 2 independent variables. And so now there are 2 partial derivatives to think about. Before we just had the independent variable time, now we've got independent variable u, independent variable v, and we can calculate partial derivatives of either one of those. So now we have not 1 chain rule to deal with, but 2 chain rules to deal with for this composite function. Because again, there are 2 independent variables. But it's pretty much the same thing. It's just instead of taking the dot product with the velocity, you take the dot product with, you might call these partial velocities. So here, this is an abusive notation, but continuing in that abusive notation, you can think of r equals to r of u and v, which is x of uv, y of, sorry, too small, y of uv. Oops, and out of the screen too. Even worse, oh my goodness, what is happening here? there we go. So sorry about that. Two independent variables, UV, and so we have these chain rules. Now let me get back to the notes because anyway. So there's our chain rules for two independent variables. Let's look at an example. Here's the chain rule written in terms of gradient notation. All right. Somehow my camera has moved. I don't know how it happened. Oh, I know how it happened. My papers got slid up the table. That's what happened. A second here. Let me make sure I'm where I should be in terms of frame. Actually, let me zoom in a little bit more. All right. So here we have z. We're thinking of z as the dependent variable. All right. Z dependent, x and y intermediate. And now u and v independent. All right. Now, if you're wondering, like, why are we looking at these things? Well, we will use all of these kinds of formulas and functions to describe curves and surfaces as we go on in the course. All right, so be patient with me. We will come to a reason for looking at these things. But I'm trying to focus just on the math here at the moment. So, so partial z, partial u is going to be partial z, partial x, partial z, partial y, and then partial derivative of x with respect to u, partial derivative of y with respect to u, which when you work it out is this and that. That's the, you might say, implicit answer, and then over here is the answer explicitly in terms of the independent variables, u and v. Likewise, partial z, partial v, we get that. All right. So, and I say once more, if we ignored the chain rule and instead directly substitute the expressions for u and v at the outset, we'd still obtain the same result. But if we're faced with extremely ugly formulas for x of uv and y of uv, this is a very useful, that is definitely not how to spell organizing, principle. Don't tell my pre-calc students. If I tell you, if I make a spelling error in pre-calc, oh my goodness, I'm in such trouble. All right, so let's see here. Next example is a little bit, what do I want to say here? So here I look at a function. It looks like I haven't told us what the function is. Z is a function of x and y. It has continuous partial derivatives at least order 2. And I tell us that the intermediate variable x is equal to r squared plus s squared, and the intermediate variable y is 2rs. So in this example, right, z is dependent, and I haven't actually made that dependence explicit, right? I just told you it's some function of x and y. All right, and then here x and y intermediate. And this time, instead of uv, I'm using r and s for independent. All right. Now, so here's what, so that's the first chain rule, and like that's all you can do. It's 2r partial z partial x plus 2s partial z partial y. I mean, you could write that partial f partial x partial f partial y there, but you can't do more than that because I haven't told you the formula for f. All right, and but you could calculate second derivatives as well, and so like when you do that, partial r of this, well, we have to do the product rule, we have to do the chain rule. So let's see here. So we get 2 partial z partial x from that term, plus, that's the first term of the product rule, plus 2r partial r of partial z partial x. So just to tell you where those are coming from, both, this is a product of functions, and so by the product rule it's giving us this, right? And then in contrast, this guy, 2s times partial z partial y, only the partial z partial y term has a possible dependence, non-trivial dependence on r. And so we can just think about pulling the 2s out, and we just get that. All right, that's what's going on there. And then of course the chain rule says that I differentiate with respect to x and then multiply by the derivative of x with respect to r, and then I differentiate partial y, the y derivative of partial z partial x, and I multiply by the y derivative, right? And likewise over here, we partial z squared partial x partial r, and then the partial y partial r, all right? And then of course things combine. You got some like terms there. So you can combine like the mixed derivatives together. Let's see here, so I finally do that down here. So there it is. All right. Can't tell if I'm out of frame or not. Nope, not yet. All right, good. So if we were to jump back to the f notation, we would have the FRR derivative is 2fx plus 4r squared fxy plus 8sr fxy plus 4s squared fyy, right? And of course I made use of the fact that we can calculate the xy derivative or the yx derivative, and they're equal. That's Clairaut's theorem. All right, so to give a less, so that's a pretty, what's the word? It's a little bit abstract, that example, right? Here's one that's less abstract. It's more kind of just explicit in the sense that I give formula for w. Here's the formula: e to the x sine y, y is equal to st squared, x is equal to log of s minus t, and we get this. Notice I've shifted now to using s and t as the independent variables. Sometimes I use u and v, sometimes I use s and t. I really want you to be able to use whatever letters there. We're not, we're not stuck on just one choice of notation here, so really context matters, We could mix it up. I mean, you could find yourself having x and y being the independent variables and u and v being the intermediate variables. That would be a tough question because a lot of students think in notation, So I don't usually do that, but it would be a fair question. But I don't think I'd like to grade it. Anyway, so here it is, chain rule. Partial w, partial x, partial s, partial w, partial y, partial s. And here's the implicit answer, here's the explicit answer, and likewise, when we differentiate with respect to t, we get this. Notice, well, I thought you said t was the independent variable. Why did you have dw, excuse me, why did you have like dw dt before, and now you've got partial w, partial t? Like, how do you know which one it is? Well, context. It's all about context. Here, there are two independent variables, so I know that ultimately, it's a function of both s and t. So when we have dependence on two variables, then we talk about partial derivatives. All right. The more fair answer to that is to be really careful. You have to take more like the approach we're taking in the analysis course and say this function goes from here to here, and this is the domain, and this is the codomain, and state things clearly. But usually, in fact, often in applications, science, engineering, and such, domains and things like that aren't stated. They're just kind of assumed from context. So, yeah. Anyway, here's another one. This time, z is equal to er cosine theta, and r is st, and theta is st. So this one, let's see. Let's say what's going on here. Z is dependent, and this time we're using r and theta as the intermediate variables, right? And we're using s and t as the independent variables. All right, And so that's why we have that chain rule, just like that. And here's the other one. The chain rule with respect to time looks like that. All right, great. So here is yet another example. This time I'm using the subscript notation. Great. Let's see here. So z is the dependent variable, x and y are the intermediate variables in this example, and s and t are the independent variables. So I'll let you read that. I think we've done enough examples here. I'll look at this example. This one's kind of good because it has, this one's a little bit more abstract. So suppose we have z is some function of x and y, all right? Notice that I've told you that f is a function from the reals to the reals, right? And it's a smooth function, which means you can differentiate it as many times as you like. And so I'm saying z is equal to f of xy. All right, so I've given you how z depends on x and y in a kind of sneaky way, right? And then if I, in addition, think about x and y being functions of time, let's see here, partial z, partial x. Oh, this is actually a, I think technically speaking, this doesn't fit into the same, I don't know if you've ever watched Sesame Street, but in Sesame Street they play this game. Which of these things is not like the other? Which of these things does not belong? This in some sense doesn't belong here. I don't know. I mean, it's not wrong. It's just not a good place for it. This is kind of this is a different type of chain rule. I see why I put it there. I mean, it is similar to the other things we're doing, but it's not quite. Anyway, so here I'm thinking of x and y being independent. And so what I'm saying is partial z, partial x would be the derivative of the function with respect to its variable, which I'm calling t. And then I have to take, evaluate that at xy, and then multiply by partial x of xy, because that's the inside variable. And so I get that. I mean, what I've written here is not wrong, but and here's how the derivative would look if you had f of xy. It would look like that. Yeah, okay. So in prime notation, it looks like this. I don't know if you can see that or not. So, yeah, all right. I don't have much more to say about that. That's just how the derivative works in that case. Now this is possibly more important. Sometimes we like to convert partial derivatives in one coordinate system to partial derivatives in another coordinate system. And so the chain rule tells us how to do that. Like if I want to convert a partial derivative with respect to the radius to the corresponding partial derivative with respect to the Cartesian coordinates x and y, then this chain rule tells me how to do it. I take my function, I rewrite r and theta as a function of x and y, and when I do that, I can understand the relation of the r derivative to the x and y derivatives as such. And the theta derivative is related to the x and y derivatives as such. And because this holds for arbitrary functions, it gives us what's called an operator identity. So since this holds for all f, it gives you the following equation. It gives you that partial r you can look at as cosine theta, partial x, plus sine theta, partial y. Now that's really a little bit different, isn't it? And similarly down here for theta, you can read off partial theta equals to minus r sine theta, partial x plus r cosine theta, partial y. Of course, you could rewrite these guys in terms of x and y, because cosine and theta is x over r, sine theta is y over r, and of course this is minus y, and that's x. Maybe I do that down here. Yes, I do. So, yeah, the boxed equations, notice I've taken and converted the cosine and sine to their corresponding functions of the Cartesian variables using the polar coordinate transformations. So, yeah, there you go. I mean, if you want to convert a differentiation with respect to the polar radius to a corresponding differentiation with respect to Cartesian coordinates, that's how you do it. And likewise for angle. Okay. Algebra challenge. Solve the operator equations above for partial x, partial y. So yeah, if you look at it, you can think of this as two equations and two unknowns, where the unknowns are partial x and partial y. And if you do that, you can solve this for partial x and partial y just as a matter of pure algebra. And when you do that, you'll get these relations. You'll actually obtain the same formulas that you would do from doing these chain rules. Like if I want to take the x derivative and convert it to a corresponding r derivative and theta derivative, chain rule says partial x is partial f partial r partial x plus partial f partial theta partial x, and likewise for y. So you're like, well, so yeah, I mean, you could start with Cartesian and switch to polars, or you could start with polar and switch to Cartesians. You can go either way, and you'll get a different chain rule for each. All right, anyway. So here's some more calculations about that. So in particular, here's what the x derivative and the y derivative work out to. If you go through these chain rules, you get partial x's, cosine theta partial r, and minus sine theta over r partial theta, and likewise here's the partial derivative in terms of y. And then sometimes, if a class has been particularly annoying, then I will make them work this homework problem. Convert Laplace's equation. So Laplace's equation, guys. Something we should talk about. Part of the reason we're talking about partial derivatives is just because most of the fundamental equations of mathematical physics and science and engineering are written in terms of partial derivatives. So one important, partial differential equation, or so-called PDE, let me write that on my other sheet. That's kind of an important bit of terminology. I should write it down here. Definition. PDE is partial differential equation. You might also hear people talk about ODE. That is an ordinary differential equation. So what's the difference between an ordinary differential equation and a partial differential equation? Partial differential equations have more than one independent variable, whereas an ordinary differential equation just has one independent variable appearing as the derivative in the equation. And in both cases, they're equations built from derivatives. And partial differential equation is an equation built from partial derivatives. So, okay, well, you're like, that's not too surprising, I suppose. Well, this is an example of a partial differential equation. It's called Laplace's equation. All right, so Laplace's equation is basically the second partial with respect to x plus the second partial with respect to y equal to 0 for some function. That's the equation that a voltage function has to satisfy in the absence of charge. It's the equation that governs like heat flow in the plane as well. So there's a lot of problems that come back to Laplace's equation. But if you were to solve Laplace's equation on like a circular or like a disk or something, then actually you'd want to convert that over to polar coordinates. And the way to do that is with this chain rule stuff I've just been talking about. And it is, it's kind of beastly, but you just take chain rules and, differentiate, and getting from here to there is about a half page or so of work. But there you go, like Laplace's equation in Cartesian coordinates changes to this corresponding partial differential equation in polar coordinates. The techniques that you need in differential equations to solve this are quite different than the techniques you need in Cartesian coordinates, and that's part of the reason we need to teach you guys more than just constant coefficient differential equations, but I guess you guys will get to that soon enough, maybe next semester, right? Okay, so this next example, basically, I don't give you formulas, I just tell you the value of derivatives and their partial derivatives at various points, and then you just kind of use the chain rule to put it together. This is a pretty good kind of test question because I can check whether or not you guys really understand the chain rule or not without worrying about whether or not you know how to differentiate things. But do study that example. It's kind of an important one. I'm sure there's homework like that too. So anyway, and then finally, here I give some examples of what's called implicit differentiation. So we'll just go briefly through these. I come back to this more in a later lecture called constrained differentiation. But sometimes you just have like an equation, in this case x squared plus y squared plus z squared equal to 3xyz, and you could think about that equation being solved. You can think about solving z as a function of x and y. Don't do it, but you could. And then you can calculate partial z partial x and partial z partial y. Now, I mean, to be fair, like x, y, and z are kind of symmetrically appearing here, right? Like, why is it that z should be dependent on x and y? I mean, that's just an ad hoc choice. But once you make that choice, you can calculate partial derivative with respect to the independent variables x and y. And it goes just like first semester calculus. You differentiate that equation with respect to x, and anytime you've got partial y partial x, well, that's 0 because they're independent, right? Partial z partial x, well, that is whatever it is. You don't know what it is, you got to leave that, and so forth. So it's just like that implicit differentiation we did in Calculus 1, but now we can do it for partial derivatives in several variables. So there's an example. And likewise, if we calculate partial y, we get that. So yeah. But I think the natural question to ask here is like, whoa, how do you know which variable you could make depend on the other two variables? And that's a good question. We'll actually come to a somewhat decent answer to that in the analysis course later on. We need something called the implicit function theorem, and you actually have to look at the Jacobian matrix and study the linear algebra of it to really come to a good answer to that. But here we can kind of calculate in the dark and just forge ahead into the unknown and just say things like z equals the function of x and y according to that equation, right? It's implicitly, the reason I say it's implicitly defined here, why is this implicitly defined? If you look at this formula right here, why do I say z is implicitly defined? It's because I haven't written z equals to a formula in x and y, right? I've written z squared. You're like, well, that's simple enough. I can just say z is equal to plus or minus the square root of that stuff. That is true. You could do that, but we don't have to because we can just use implicit differentiation to discover partial z partial x is that, and partial z partial y is that. And there are lots of equations that are implicitly defining z where you couldn't solve for z, and yet you can still calculate the partial derivatives, because when we partial differentiate an equation, we always get something linear in partial z's, and so you can solve for them. Here's another example, So, oops, let's scooch down here a bit. So I don't know about you, I can't solve that for z, right? Can you solve this? Can you isolate z? I know I can't. I cannot solve that. I cannot solve this for z. And yet, with the idea of implicit differentiation, I can discover how z changes with respect to x by calculating this implicit derivative. So like partial x of x, partial x is 1, then minus partial x, then the derivative of inverse tangent is 1 over the argument squared. And then chain rule says I still have to multiply by partial x of the inside function, which here is yz, so y is constant because it's independent with respect to x. I pull that out, and I'm left with partial x, and then I solve. There's a little bit of algebra here, solve for partial x to get that. And like I said, I omitted some algebra in that implication above. And likewise for that one. All right, so we're getting near the end here of the part which is most important for us at the moment. So next up, as I mentioned at the end of this section, I'll talk about derivatives of vector valued functions. Here, what I do is attempt to show you in terms of the general derivative how these rules are coming from multiplying the Jacobian matrices. So like, for example, if we look at W being f of x of st, then the chain rule of advanced calculus says you multiply the derivative of the Jacobian of f times the Jacobian of x, and when you do that, you get these chain rules that we've been using. So all of these chain rules are really ultimately just born of matrix multiplication of the Jacobian. I'll just say that. I don't really expect you to derive that or anything. And here's the corresponding tree diagram for functions of two independent variables. Let me see if I can find it in my notes. I got some color coding, of course. Come on. There we go. Ooh, I will not try to recreate the color coding on page 202. See page 202. Okay. See page 202 for coloring. But basically I explain through some color coding like how we get the partial w partial s versus the partial w partial t. But again, it's basically whatever. I'm gonna shut up about that. The last few examples here we'll come back to later. We'll need to come back to these later when we study the coordinate change problem for surface integrals. So I don't really ever need it until there, but so I just say it'd be good if you read through these, and you might need to read through these. I probably have a homework problem on them, but I would say that the material before this point in this section is much more important. All right. But yeah, if you've got a function of if you have a vector of functions where a, b, and c are all functions of x, y, and z, and then so like you have intermediate variables x, y, and z, and those intermediate variables are written in terms of independent variables u and v, then you get like you differentiate each one of these component functions by the kind of chain rule we talked about before, and so you can organize those in particular as like you can look at what partial a partial u is in terms of these dot products. But anyway, I don't really have much to say about that. But I think they're cool formulas and stuff. But here's the chain rule for functions of n variables. This is here is an example with 3 independent variables. If you wanted to see what that looks like, there is what it looks like. So yeah, and this one. So yeah, you can read the rest of the examples. I don't think they're probably just more of the same. If I know myself, Anyway, I hope that helps you get started on chain rule.